We are discussing the basic concepts of electrochemistry, in which today we are going to discuss the Kohlrausch law. And in previous lecture we have discussed about the electrical conductance, which is of three types known as specific conductance, molar conductance, and equivalent conductance. The specific conductance have unit of per ohm per centimeter, whereas the unit of molar conductance is per ohm centimeter square per mole, and the equivalent conductance have unit of per ohm centimeter square per gram equivalent. So now let's discuss the factors determining the conductance of an electrolyte. And the conductance of electrolytes depends on the following factor, in which the first one is nature of electrolyte. The second factor is temperature. And the third factor is concentration. So here we are going to discuss the relation of the concentration of electrolyte with the specific conductance and the equivalent conductance. The specific conductance decreases with dilution. The reason is that the number of the current carrying particles like the ionic species per centimeter cube are decreasing so ions per centimeter cube of solution become less at low concentration due to the dilution. So here no doubt the degree of dissociation increases with dilution. So the degree of dissociation increases with dilution, but the number of ions per centimeter cube are decreasing to such an extent that even a complete dissociation does not produce as many ions per centimeter cube are present as before dilution. So here ions per centimeter cube are decreases with dilution. So the degree of dissociation have lower impact on the specific conductance as compared to the number of ions available in the electrolyte solution. In contrast to the specific conductance, the equivalent conductance increases with dilution. So we have two important points here. and finally attains a maximum value at infinite dilution. So what is infinite dilution here? It is the theoretical dilution limit which is usually obtained from the extrapolation of the plots, and this dilution is near to the negligible amount of the solute, that is electrolyte. So what's the reason that the equivalent conductance increases with dilution? So the reason is that the equivalent conductance is the product of the volume of the solution containing 1 gram equivalent of the electrolyte. One gram equivalent of electrolyte. According to the formula, we have to add a specific amount of the electrolyte to make overall volume to 1 decimeter cube. So smaller the amount of electrolyte, greater will be the amount of solvent volume required for the compensation of overall volume. Conversely, it is clear from the formula of equivalent conductance that the greater the amount of equivalent conductance of the electrolyte solution with smaller value of denominator, so the smaller or the dilute concentration will have higher value of equivalent conductance. So in order to have a clear picture of these two important points, let's discuss the variation of conductance with concentration of strong and weak electrolytes. So as we have discussed that the equivalent conductivity of an electrolyte increases on diluting the solution. So here we have the diagram showing graphs between equivalent conductance and the square root of the concentration. And we have 3 examples of the electrolytes. And we have 2 strong electrolytes known as HCl and KCl. HCl is an acid, and whereas KCl is a salt. So here the value of concentration is higher, and if you move from the higher concentration towards lower concentration, the equivalent conductance is increasing to a maximum limiting value at which solution is so dilute that the concentration approaches to 0. So these are the equivalent conductance of the HCl and KCl at infinite dilutions. So let's the value of HCl at infinite dilution is around about 250, whereas it's above 150, around about 175 for KCl. So this level of dilution cannot be obtained practically, so we need to take the different concentrations of the electrolyte, and the respective equivalent conductance can be plotted, and it can be extrapolated to get the value of equivalent conductance at infinite dilutions. Now come to the case for the weak electrolyte. In the case of weak electrolytes like acetic acid, there is no limiting value of the equivalent conductance even the concentration approaches to 0. So for the case of weak electrolyte, the limiting value of the equivalent conductance, that is for infinite dilution, cannot be obtained from the extrapolation of this plot. And the conductance of a solution depends on the degree of ionization. So here alpha is the degree of ionization. It means the extent of the number of acetic acid molecules that are ionized into respective positive and negative ionic species. And here the degree of dissociation increases with dilution, so the equivalent conductance is increasing exponentially. At higher concentration, the degree of dissociation is less than 1, but at infinite dilution or near to the infinite dilution, the degree of dissociation is equal to 1. It means that all the molecules of the acetic acid present in the solution have been ionized to the respective ionic species. So here we can say that the degree of dissociation represented as alpha is equal to 1 when all the species are ionized means all the molecules have been dissociated into respective ionic species. As for the case of the acetic acid, the acetic acid molecules have been ionized into acetate and hydrogen ion. For strong electrolytes, for example HCl and KCl, all the HCl molecules are ionized into hydrogen ion and chloride ions. So for this case, the degree of dissociation is nearly equal to 1. It means that all the species have been ionized. Whereas for the case of weak electrolytes, as we have discussed about the acetic acid, the degree of dissociation is less than 1 for specific concentration. So here we can represent the equation with equilibrium equation. That's because the ionic species are reformed into the molecular species. In the diagram we can see that by increasing the concentration, the degree of dissociation is less than 1. For the weak electrolyte, it means that the number of ionic species available within the solution, which are important for the conductance of the current through the solution, are decreasing with increasing concentration. Whereas at very dilute solution, when the concentration of the acetic acid is very small, at this condition the number of molecular species are ionized into the ionic species, and these ionic species are available for the conductance of electricity. So the conductance or equivalent conductance increases at the infinite dilution. So for the case of weak electrolytes, we can write the degree of dissociation as the ratio of equivalent conductance over equivalent conductance at infinite dilution or at zero concentration. So here we can see that the degree of dissociation can be calculated using formula given here. So the value of this equivalent conductance at infinite dilution cannot be found from direct extrapolation of the plot. For this purpose we need to discuss the Kohlrausch law, that is the law of independent migration of ions. Kohlrausch law can be understood from the studies which were carried out for the strong electrolytes, where the value of the equivalent conductance at infinite dilution can be calculated from the extrapolation of the plots. As we have discussed that the equivalent conductance depends on the degree of dissociation, and let's discuss a point, that is when we have a potassium ion having a similar concentration in aqueous solution, and if we replace these potassium ions with sodium ions, we can see that the value of equivalent conductance at infinite dilution decreases to a factor of 23.41. It means that the value of equivalent conductance for potassium ion at infinite dilution is 23.41 times higher than for the case of sodium ion when their chloride salts are used. So from here we can see that the value of equivalent conductance for these two species when their chloride salts have been taken, it doesn't depend on the anionic species but depend on the these two cationic species. Similarly, if we change the anionic species from the bromide to chloride, the equivalent conductance for the bromide is higher as compared to chloride with a factor of only 2.06. So the equivalent conductance of the bromide ion is 2.06 times higher than the chloride ion when keeping the cationic species constant, that can be a potassium or sodium ion. So keeping this experimental information in mind, Kohlrausch law was devised. So Kohlrausch gave the following law, that is at infinite dilution each ion makes a definite contribution towards the equivalent conductance of the electrolyte irrespective of the nature of other ions. It means that if we take the potassium, a comparison of potassium ion and sodium ion, and by taking the any other anionic species, the difference of the total equivalent conductance at infinite dilution will be equal to nearly 223.41. So it means that when we take potassium chloride and sodium chloride, the difference will have the 23.41, and if we take the potassium bromide and sodium bromide for comparison, we need to take the counter ion same. By keeping the counter ions same, we can differentiate the role of the potassium and sodium ions. So here the basic difference is due to the behavior of these two ions. Similarly, for the comparison of bromide and chloride, we need to take the counter ion, that is the cation, which can be either potassium or sodium. For a comparison, we need to take the cationic species same for these two species. So for example, for potassium bromide and potassium chloride, the difference of the equivalent conductance at infinite dilution will be 2.06, and this difference is smaller as compared to the difference of the equivalent conductance at infinite dilution for the potassium and sodium ions. So it means that the role of the contribution of the equivalent conductance from the respective ionic species is different, which is not affected by the nature of other ions with which it is associated. So here we can write the mathematical expression for the Kohlrausch law, that is the equivalent conductance of the electrolyte is equal to the equivalent conductivity or the conductance of the cationic species and anionic species at infinite dilution. So capital lambda is showing the equivalent conductance of electrolyte as whole, whereas the small lambdas are showing the equivalent conductance of cationic and anionic species at infinite dilutions. So here small lambdas are known as ionic conductances, and this law is valid for any dilution, but it is mostly applied for infinite dilution. Moreover, the ionic conductance of an ion is fixed at a given temperature, so whatever might be the nature of other ion associated with it, it means that the nature of the sodium ion will have a specific contribution towards the overall equivalent conductance of the electrolyte, irrespective of the any other anionic species attached to it, which have its own contribution. So let's discuss an example. For example, if we have a salt that is AB and we have their molecular formula. So here the equation have been stoichiometrically balanced, and the cationic species have a charge plus y and anionic species have a charge minus x. For this kind of equation we can write the Kohlrausch law. The total equivalent conductance of the solution at infinite dilution is equal to the stoichiometric factor into the equivalent conductance or the ionic conductance produced by the species A into, so we have to add the contribution of the other species, that is the anionic species, where y is the stoichiometric coefficient, and we have the anionic conductance. So let's write the equivalent conductance at infinite dilution for the case of sodium chloride. For sodium chloride we have monovalent species, sodium ion and chloride ion. For this case we can write the equivalent conductance as that's for sodium ion and chloride ion, whereas for the case of barium chloride we can write the equation, that is barium plus 2 chloride ions. For this kind of salt we have the Kohlrausch law is written as, that is the ionic conductance of barium ion and chloride ions. So this law is true for the molar conductivity, and similarly we can write the molar conductivity of the solution, that is the electrolyte solution, is at infinite dilution is equal to the ionic conductance of the cationic and anionic species separately. Using this law, we can calculate the equivalent conductance of weak electrolyte at infinite dilution, as we have discussed earlier that we cannot prepare the electrolyte solution at infinite dilution, but the value of this equivalent conductance at infinite dilution is usually calculated from the plots which are extrapolated towards y-axis at nearly zero concentration of electrolyte, but as the weak electrolytes are showing the exponential increase in the equivalent conductance at lower concentration, that is near to the infinite dilution, but we cannot measure the equivalent conductance at infinite dilution, is similar to the solution like we have 1 kilogram of water and we have added a grain of salt. So this mole value of the electrolyte cannot be measured through the measurement of the electrical conductance using instruments. So it's the instrumental limitation. So we can use this law to calculate the equivalent conductance of weak electrolytes. So let's see how we can calculate the equivalent conductance of the weak electrolytes at infinite dilution. So for this purpose we need to carry out the indirect measurements. For example, for the measurement of the equivalent conductance of the acetic acid at infinite dilution, we need to measure the conductances for the strong electrolytes containing the ionic species which are also present in the weak electrolyte. So for this purpose, for the calculation of the hydrogen ions, their equivalent conductance can be measured from the HCl, and for the case of acetate we can measure from the acetate salt. And as we have measured the equivalent conductance of the full electrolyte, we cannot measure the the ionic conductance of one anionic or cationic species, because we have the electrolyte which is actually giving the value of the conductance, that is the combination of cationic and anionic species. So let's see how we can calculate the conductance for the acetate or the acetic acid. So for this purpose, let's take three kind of the electrolytes. First is potassium chloride. The equivalent conductance of potassium chloride is the combination or the summation of the equivalent or ionic conductance of potassium ion and chloride ions. Whereas for the case of potassium acetate, the equivalent conductance of potassium acetate is actually the ionic conductance of acetate and potassium ions. For the case of HCl, the equivalent conductance is actually the combination of ionic conductance of hydrogen ion and the chloride ion. So let's see how we can calculate the equivalent conductance of the acetic acid. For this purpose, we have to add the conductance or the ionic conductance of the acetate ion from the acetate salt and hydrogen ion from the HCl. So we are going to add the value of the ionic conductances of hydrogen ion and acetate ion, and we need to subtract the values for the potassium and chloride ions. For this purpose we will subtract the value of equivalent conductance of the potassium chloride. So by putting the values of the ionic conductances of each ionic species that have been generated from the respective strong electrolyte species. So here the ionic conductances, and in this one these are the molar or equivalent conductances at infinite dilution. So here we can see that the contribution of chlorides and potassium can be cancelled out. So overall we have the contribution of the ionic conductance of acetate and hydrogen ion. So in this way we can calculate the equivalent conductance of weak electrolyte from indirect method by measuring the equivalent conductances of the strong electrolytes containing the ionic species which are common for the weak electrolytes. Another important application of Kohlrausch law is that we can calculate the alpha, that is the degree of dissociation. So here we can calculate the value of degree of dissociation, that is actually equal to the ratio of the equivalent conductance over equivalent conductance at infinite dilution, or it can be equal to the molar conductance over molar conductance at infinite dilution. So the value of the molar and equivalent conductances can be calculated from the indirect method as explained for the case of acetic acid, and here the values of equivalent and molar conductance can be calculated from the experimental method by taking any concentration of the electrolyte species. So for this specific values of the equivalent or the molar concentration of the electrolyte, we can calculate the degree of dissociation. So here we can calculate the degree of dissociation of weak electrolytes for the variable concentration of the electrolyte in the solution.